Previously, we learned how to find the inverse of a general function given its equation. In this lesson, we are going to focus on how to find the inverse if the equation we are given is a radical function. And by radical function, all I mean is we've got some expression, f of x, that is under a square root. So we're going to learn how to find the inverse functions for things that look like this. So there's 3 steps to this process. First step, we need to find the range of the original function given. Then step 2 is we need to replace the function description and function notation just with y for easier things and solve for x. And then the final step, if necessary, with this new inverse function that we found, restrict the domain of the inverse function to the range of the original function. So in step 3, we've kind of got to look back at what we found in step 1. So let's see this worked out with this example. Restrict the domain and then find the inverse of the function f of x is the square root all of x minus 4. So step 1 asks us to determine the range of the original function. And to do that, let's think about what a general square root function does. If we've got the general square root, f of x is just the square root of x, so different than what we're looking at, we know its graph looks something like this. So notice, as the x values increase, we see the y values, the range increases. So here, for this general function, the range is 0 to infinity, because as the x values progress, we will pass through all positive y values, and we started at the y value equal to 0. But what is our expression, and maybe I'll call this g of x, since this is f of x. What does f of x equals the square root of x minus 4 look like? All this does to the function is it just brings it back 4 at the start, but it still has the same general shape of the square root function. So this is our f of x. So notice the range is the same. It's still every y value from 0 to infinity. Another way you could reason about that is we know that for a square root, the interior has to be positive. So the smallest the interior could ever be is 0. And we know when x is 4, the y value is 0. And then as our x value increases, the y values are just going to increase and get higher and higher positive numbers. So that's kind of 2 ways of how we could think about the range of this function, either by reasoning based on its graph or by its equation, what we know about square roots. So the range starts at 0 and it goes to infinity for our function f of x equals the square root of x minus 4. So that's step 1. Now in step 2, we need to replace the f of x just with y. That just helps us think of solving this a bit more easily. So in step 2, we will solve, we've had this equation, but as before, we need to switch the x and y values. So that would give us x equals the square root of y minus 4, and we're going to solve to get y by itself. So whenever we want to get y by itself, first we see it's inside this square root. So the only way we can get into the y is if we first get rid of the square root. So if you square a square root, the exponents cancel out and just leave us with exponent 1. But what's done to one side must be done to the other side. So we've got x squared equals the square and the square root cancel out perfectly, and we're just left with my y minus 4. Add 4 to both sides, and we get y equals x squared plus 4. Now this is our inverse function, so we really should call it f inverse, because it's the inverse function of f. But here's the thing, this inverse function, x squared plus 4, if we were not thinking of it as an inverse function to the original, but I just separately, new problem, asked you about its domain, what would be the domain of this problem? Again, not as an inverse, just a general x squared plus 4. Think about it and write it down. we know that x squared plus 4 is just a parabola that's been shifted up 4. So its domain is all x values. But since we're dealing with a function who has a restricted domain and range originally, then their inverse should also be restricted, because we know the range of the original function is by definition the domain of the inverse function. So even though our inverse function by itself is fine for all positive values and negative values, since it's the inverse of something that has a range restriction, we know its domain must be restricted. So its domain is really from 0 to infinity. So even though the function itself can exist for negative values, since it's the inverse of a function that has a restricted range, domain and range is switched for functions and their inverses, so this function's domain must be restricted. And that's how we would answer that here. We would say, okay, the inverse function is this, but on a restricted domain. Why is it restricted? Not because of the function itself, but because of which function it's the inverse of. That's the only topic from 3.8. We just need to practice using these 3 steps and recognizing when to use it for a radical function. So let's now turn to 3.7. In this video, we're going to look at rational functions. Now, rational functions are any expressions that have one polynomial divided by another polynomial. And the specific thing that we want to focus on is, since a rational function involves a fraction, we know the denominator of the fraction can't be equal to 0. So if we're asked what is the domain of a rational function, we would need to make sure that the polynomial in the denominator is never 0 for that to be in the domain. Now let's look at a few examples of rational functions. This is a rational function because we've got the polynomial x divided by the polynomial x plus 1. This is a different rational function because we've got the polynomial 2x divided by the polynomial x squared plus 2x plus 1. And also the function 1 over x is a rational function because any constant could be seen as a polynomial divided by x, which is also a polynomial. Now, we've probably had most exposure to 1 over x, so let's look at it for a bit to help us understand the general behavior of rational functions. Here's a table of certain input values with their corresponding output values for 1 over x. So for instance, 1 divided by negative 0.1 is negative 10. 1 divided by negative 0.001 is negative 100, and it continues. Notice the trend. These x values are getting closer and closer to 0 from the left, but do we see the y values are getting farther and farther negative? And not only are they getting more negative, but significantly more so. Here we went from negative 0.01 to negative 0.001, but the y values jump from negative 100 to negative 1,000. Now as we look at the next table of values, we've got the positive version of these inputs, so 0.1, 0.01, etc. And notice that as we get the x values going towards 0 from the positive direction, the y values just keep increasing. And I would say they even increase more and more without bound. Okay, all of that together makes sense when we look at the graph of 1 over x, which we can see here. Notice that for values as x gets large, for instance at like x equals 10, we know 1 over 10 is 0.1. So as the x values get larger, the y values should get smaller, closer and closer to 0. Same here, as the x values get further negative, the overall y value should get smaller because 1 over a big number is a small number as a fraction. However, as the x values approach 0 from the left and the right, notice the y values as we approach through negative values are getting more and more negative. And as we approach through y values or x values to the right of 0, the y values are getting larger and larger. And specifically, we know that there is no value for the function when x is 0, because that would involve 1 over 0, which we know does not have a value. So if we were looking at the domain of our function f of x, it would be all values before 0, but not including 0, union all values after 0, but not including 0. Specifically, we've got a vertical asymptote at 0, and the thing to notice is at x equals 0, that's where the denominator of our function equals 0. So for rational functions, wherever your denominator equals 0, that's going to give us a vertical asymptote like we see here in our general 1 over x graph. Now here we've just got some symbols that you might see. This should be read as x, the arrow should be go approaches, so as x approaches the point A, and then the superscript with the negative symbol is from the left. So as x approaches A from the left, as x approaches A, and the plus should be read as from the right. And what this means is if we were looking as x approaches 0 from the left, we'd be looking at x values that get closer and closer to 0 through values from the left, so negative 0.1, negative 0.01, negative 0.0001. So think about it this way. As x gets closer to 0 from the left, as x gets closer to 0 from the right, we'd still be steadily getting closer to 0, but through positive values. So maybe from 0.1 to 0.01 to 0.001. This is x approaches positive infinity. So our x values are going out to positive infinity in that direction forever. As x approaches negative infinity, x is going out in this direction forever. The output values approach infinity. That would be when the output values are getting higher and higher. The output values f of x are approaching negative infinity. That's when the output values are getting lower and lower. And f of x approaching a is just the output values approaching some fixed y value. Okay. And these symbols are just a quick way that we can express behavior of functions. So for instance, as x goes to some value, this is behavior of the y values. So let's look at the definition of vertical asymptote. We have that a vertical asymptote of a graph is a vertical line at x equals some a value. So fix x value, that's where the vertical asymptote is. And at this x equals a, the graph of the function will go towards positive or negative infinity about that vertical asymptote, which we could write as this. As x gets closer to the point A, the output values are approaching infinity, or as x approaches a, the output values could be approaching negative infinity. Now we just saw an example of our first vertical asymptote in the 1 over x equation. For the function 1 over x, it looks something like this. So notice we could say as x approaches 0 from the left, so as we're going to 0 from the left through negative values, what can we say the output values, what are they doing? Notice as x gets closer to 0 from the left, the output values get farther and farther negative, so we would say it approaches negative infinity. And as x approaches 0 from the right, f of x approaches, okay, I'll give you a second to write in what you think is here. As we approach 0 from the right, the output values are getting larger and larger, so they're going to positive infinity. So if we're given a rational function, how do we identify vertical asymptotes? First, you should factor the numerator and denominator. Then you should note restraints in the domain of the function. Since our functions are always rational functions, that's what we're looking at here specifically in this case, this is when the denominator equals 0. That's the restrictions in the domain. And then step 3 is you reduce expressions by canceling common factors. because these common factors are actually wholes, and we'll talk about them in a second. But any common factor that's in the top and the bottom, we can cancel that and see that as our whole. And any value that causes the denominator to be 0 in the simplified version after we've canceled out common factors, these are where the vertical asymptotes occur. So let's look at our first example. We're asked to find the vertical asymptotes of this rational function, polynomial divided by polynomial, if they exist. Now, the top part of the polynomial is fully simplified, but we could factor the bottom. For instance, we see that as a difference of perfect squares. It's of the form something squared minus something squared. And by difference of perfect squares, that always factors to be just x plus y, x minus y. So in our case, we've got x squared minus 2 squared. So this would factor to be x plus 2, x minus 2. So writing that out, we've got our k of x. And we're doing step 1, factoring the numerator and denominator if necessary. Okay, and what are our domain restrictions? That's step 2. We're going to be looking for when is the denominator equal to 0. Now the denominator, this whole expression, is only equal to 0 if this term equals 0 or this term equals 0, right? Because if one of them equals 0, then they multiply and the whole term goes to 0. So we'd want to think about, well, when is x plus 2 equal to 0? When is x minus 2 equal to 0? This gives us at x equals negative 2. This gives us at x equals 2. So the domain means we can't have these, right? We don't want these to be equal to 0. So the only restrictions are we can't be at negative 2 or positive 2, but we could be anywhere before, between, or after. So that's going to be from negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. So we finished step 2. Now step 3 says reduce the expression by canceling any common terms, and specifically, do we see that we've got an x minus 2 and an x minus 2 above and below, so we're going to cancel those. And we get the expression 1 over x plus 2, because actually at x equals 2, we've got a whole. We'll talk about y in a second, but we can reduce our function to just 1 over x plus 2. And now in step 4, anywhere that causes the denominator to be 0 in the simplified term is where the vertical asymptote. So we've got a vertical asymptote at this term is 0 at negative 2. And that's the only thing that makes the denominator 0 in the simplified term. So that's how you would go through and find the vertical asymptotes of a rational function. Next, we're going to identify removable discontinuities in a rational function. These are also known as wholes. So just the structure of this lesson so far is rational functions have a lot of interesting behavior in their graphs, and we are learning how to look at each piece of that and how to find it based on the equation. So next up is wholes or removable discontinuities. A removable discontinuity occurs in the graph of a rational function at a certain x value if that x value is a 0 for both the denominator and the numerator. So we saw this in our previous example. There was a x minus 2 term in common in the top and the bottom of the fraction. So at x equals 2, what made both of these equal to 0, we would have a whole of the graph, or a removable discontinuity. So that's how you would find these. And we'll talk about what multiplicity means once we start graphing these. I think it's easier to see in context. Now, if you're given a rational function, how would you find horizontal asymptotes? That's another aspect of their graphs. To identify the horizontal asymptotes of a graph, there are basically 3 things we need to look at. It's all about comparing the highest power of the exponent of the top or the bottom of the fraction. So for instance, if the degree of the numerator, the top one, is less than the degree of the denominator, then you know the horizontal asymptote is guaranteed to be at y equals 0. So if the numerator is smaller than the denominator, the horizontal asymptote is at y equals 0, and an example of this is 1 over x. The rational function 1 over x, the numerator's highest power is actually x equals x to the 0, because x to the 0 is 1, whereas the denominator's highest power is x to the 1, because that's just x. Notice this exponent is larger than this exponent, so we're in this case. And if we look at the graph of 1 over x, we see indeed there is a horizontal asymptote at y equals 0 along the x-axis. So 1 over x is our classic example of when a rational function has a horizontal asymptote at y equals 0. Next, if the degree of the numerator is instead larger than the degree of the denominator, then there is no horizontal asymptote. Okay. Now, if the degree of the numerator and denominator are equal, then the horizontal asymptote occurs at the ratio of the leading coefficients. We'll see an example of this. But notice with a rational function, you've got some polynomial divided by another polynomial, so there's only 3 cases. Either the leading exponents are equal, in which case we can find the horizontal asymptote based on the ratio of the leading coefficients, or the exponent of the numerator is higher than the denominator, so there's no horizontal asymptote, or the exponent of the denominator is higher than the numerator, in which case the horizontal asymptote is at y equals 0. Let's work through some examples related to this. Okay. So for example 1, notice we've got 6x cubed minus 10x divided by 2x cubed plus 5x squared. So let's find the highest degree on the top. So on the top, we've got an exponent of 3 on the first term and an implied 1 on the second term because x is just x to the 1. The highest of these is 3. In the denominator, our first term has a power of 3. Our second term has a power of 2. Pick the highest. So which of these 3 cases are we in for example 1? Take a moment to identify it. In this case, the highest power is equal on the top and the bottom. So we have a horizontal asymptote, and it will be equal to the ratio of the leading coefficients. Now, what does the ratio of the leading coefficients mean? All it means is that you isolate the highest power term on the top, the highest power term on the bottom, and you look at what number is getting multiplied by the x term. So in the top, we've got a 6 getting multiplied by our highest term x cubed. And on the bottom, we've got a 2 being multiplied by our highest term x cubed. So the horizontal asymptote is at y equals 6 over 2. And if this can be reduced, we will. So this is at 3. So the horizontal asymptote is at y equals 3. And notice we just took the coefficient of the highest term in the top and divided it by the coefficient of the highest term in the bottom. Now, it's the same instructions. Oh, we also need to find the vertical asymptote. And for this example, let's not find the vertical asymptotes here. Let's erase that part. We've got a lot of practice with that coming up. Let's just focus on the horizontal asymptotes. So I'm just changing the examples prompt to just find the horizontal asymptotes. Why don't you attempt problem 2 on your own? So pause the video now, find the horizontal asymptotes of the function k of x if they exist. Unpause when you're ready to check your work. Now looking at the numerator, we see the highest term is the first one, x squared, followed by 4x. So this is the highest term in the top, and its power is 2. That's its exponent, x squared. Looking at the denominator, between the x cubed and the minus 8 term, this is the highest power, and its exponent is 3. So which of these 3 options are we in for the horizontal asymptote? Visualize that. Okay, so we're in the case where the numerator, the top, is smaller than the bottom, So we're guaranteed the horizontal asymptote is just at y equals 0. And the only one we've seen this case and this case in the example. The next case would be if the horizontal asymptote was not there, we would have to have a larger power on the top than the bottom. So for instance, maybe x to the fifth plus 2 divided by x, this would have no horizontal asymptote, which can be abbreviated HA. Vertical asymptote can be abbreviated VA, because the exponent of the top is higher than the exponent of the bottom. Previous to this, we've looked at separate pieces of the rational function. We've looked at how to identify the vertical asymptotes, how to identify the horizontal asymptotes, and then even holes. And also we've looked at the domain of rational functions. Remember, rational function is just polynomial divided by other polynomial. Now let's put all this together to help us graph rational functions. Now there's a lot that goes into the graph of a rational function, so I recommend that you write down these steps if you don't have the paper with you, and keep these handy as you go through our homework problems, just to practice knowing each step what you do next. I'll read through these and then we'll go to our first example. I recommend that maybe the first thing you do is you find the y-intercepts of the function if they exist. Then you would factor the numerator and denominator. Now, factors in the numerator that are not common to the denominator are going to help us find the x-intercepts. We'll see examples of this. And let's add something. At step 2, you might write down the domain of the function once you have it factored. That's going to be important to have. Step 4 would be to find the multiplicities of the x-intercepts to determine their behavior. We'll talk about exactly what this means within our examples. Factors in the denominator. Note the multiplicities to find the vertical asymptotes. Okay. Also identify if there's any holes or removable discontinuities by looking if there's common terms in the numerator and denominator. Then you're going to look for the horizontal asymptotes by comparing the degrees of the numerator and denominator. And then finally, with all this information neatly gathered to the side, you would begin to sketch the graph. So with these graphing rational function problems, the majority of your time should be spent gathering all of this information. I'd say maybe close to 70 or 80% of your time on the problem is all of this beginning work, keeping it nicely organized. And then the final step is just putting it all together. But if you've gathered all this clearly, putting it together is going to be much easier. So remember, most of your time is spent finding these, and then the graphing is just the final stage. In this example, we're asked to graph our function f of x equals x plus 2 times x minus 3, all divided by x plus 1 squared times x minus 2. And nicely for us, we see we're already given the expression in factored form, so we don't have to worry about factoring it in this case. We just need to find all the pieces of information and then put them together in our graph. So even though this graph is here, we are not going to use it until we've got all the information listed. I think the main error that students have in these type of problems is trying to graph too soon. And if you don't have all the information laid out in front of you, you're going to start graphing it wrong, and it's going to be hard to correct your work. So for now, pretend that this does not exist and we're just going to find all the pieces of information and then use it. Looking back at our list, let's do step 1. We're going to evaluate the function at input values equal to 0 to find its y-intercepts. Remember, for y and x-intercepts, at a y-intercept, the opposite thing, x is 0. At an x-intercept, y is 0. So remember, x and y-intercepts, they just switch what's 0 based on what it's called. Y-intercepts, x are 0. So we're going to let x be 0 and see where this function has a y-intercept, where it crosses the y-axis. And I'm going to label this the y-intercept. There's going to be a lot of information, so if we can be organized, we're going to be able to call on all that information to get our final graph. So at y-intercepts, I know x is equal to 0, so plugging that in for our equation, f of 0. everywhere there's an x, replace it now with 0. Okay. 0 plus 2 is 2. 0 minus 3 is negative 3. 0 plus 1 is 1. When squared is 1. 0 minus 2 is negative 2. Watch your signs here. So this would be negative 6 divided by 1 squared is 1 times negative 2 is negative 2. Negative 6 divided by negative 2, negative divided by negative is positive, so that would be 3. So we've got the y-intercept at 0, 3. That's one of our first key points. And I'd recommend even boxing or doing something to help you see this piece of information later very clearly. Now let's look at step 2. Step 2, factor the numerator and denominator and find the domain. Now ours is already factored, but we still can write down the domain of this rational function. Now thinking back to the problems that we did in finding the domain of the function, remember you're looking for places where the function would have issues. Polynomials in themselves have no issues, but where the polynomials are as a location could have an issue. For instance, since our function's a fraction, we know fractions have problems when the denominator equals 0. So we need to look at the terms in the denominator and ask ourselves, are they ever equal to 0? Because those would be places we'd have to exclude from the domain. So we want to make sure the denominator does not equal 0. Now this could only equal 0 when each term separately equals 0 from multiplication. For instance, if this term was 0, 0 times anything is 0. Or if this term was 0, 0 times anything is 0. So that allows us to split the problem into a simpler equation. We just have to think about when each term separately equals 0. Now this one, so we want to make sure x does not equal 2. And the next place, remember, x plus 1 squared can only equal 0 if it was 0 before it was squared, right? Because squaring something doesn't make something 0. So x plus 1 squared not equaling 0 really simplifies to x plus 1 not equal 0. Because the interior has to be 0 before squaring it gives it to be 0, if that makes sense. So this excludes when x is negative 1. If we subtract 1 from both sides, we'll see that. So x can't be negative 1, x can't be 2. That's the only domain restrictions because this function has no other issues. So if I'm looking at this on a number line just to help me write out my interval notation, I've got negative 1, positive 2. I can't be these places, but I could be anything before negative 1, anything between negative 1 and 2, anything after 2. So actually, why don't you pause the video now and write down the domain on your own? Unpause to check your work. Okay. So we can have from negative infinity to negative 1 not including it, union negative 1 to 2 not including it, and then 2 to infinity not including 2. So that's going to be our domain. So next would come step 3. Let's go back to our list. Step 3 means find the x-intercepts. So here we're going to look for when y is 0, what is the corresponding x value? And visually this is going to be where the function crosses the y or the x-axis. Now for y-intercepts, you know that's where y is 0. Now y is the output of the function. So we're looking to solve when is this equation true? Okay, so 0 is equal to this expression. What x value makes this true? Now first, as we look at the structure of the right side, do we see it's a fraction? So we want to ask ourselves, what type of fractions end up equaling 0? What do you have to know about the top or bottom for the overall fraction to be equal to 0? Think about what fractions simplify to be 0. The only fractions that simplify to be 0 are those fractions where the top number is 0 and the bottom is any other number except 0. So for instance, 0 over 2 is 0, 0 over negative 100 is 0. I think we're getting the pattern. When you're asking yourself when a rational function equals 0, that really simplifies to asking when is the numerator of the function equal to 0. Okay. So this simplifies to solving when is this equal to 0. Now we've got a product of terms equaling 0 that only happens if the terms separately equal 0. So this is equivalent to asking us when is x plus 2 equal to 0, when is x minus 3 equal to 0. This is when x is negative 2, and this is when x is equal to positive 3. Now the one thing you want to watch out for is you want to make sure these x-intercepts are actually in the domain, because if they're not in the domain, they're not x-intercepts. They would be holes in that case. So looking here, negative 2 is in this portion of the domain between negative infinity and negative 1, so that checks out. Positive 3 is in this portion of the domain between 2 and infinity. So both of these are x-intercepts. So we're going to write down our x-intercepts here. At negative 2, x value, the y value is correspondingly 0. That's what we found. At 3, the y value is correspondingly 0 as well. So we found our two x-intercepts. Now let's look at step 4. Step 4 is to use the multiplicities of the x-intercepts to determine their behavior. I'm going to say this is what we're going to do while we're graphing. It's easier to do in the moment, but we are going to remember that we need to think about these multiplicities. Again, that will be discussed when we start graphing it. So then step 5, find the vertical asymptotes. We know vertical asymptotes occur when the denominator is equal to 0. So for vertical asymptotes, you're looking for when is the denominator equal to 0, so long as it's not also a term on the top. So in our case, none of the terms cancel out. They're all distinct. So we want to look for when is x plus 1 squared equal to 0. Now that's already work that we did with our domain. We found that was at x equals negative 1 and x equals 2. That's where the denominator equals 0. We could do the work again if we wanted to, but we kind of already found out our domain. We know that's at x equals negative 1 because it makes the bottom term equal to 0, and x equals 2 because it also makes the denominator equal to 0. So we've got these two vertical asymptotes. We'll move to step 6. Step 6 is our last step before, step 6 is our last step before we put it all together. We should also think if there's holes of the graph, but our function did not have them, and I'll show why in a second. And then we'll do horizontal asymptotes, and we'll be ready to combine it all together. Now, the reason our graph had no horizontal asymptotes is notice the term x plus 1 did not appear in the numerator, nor did the term x minus 2. So holes only occur when you've got a repeat term in the top and the bottom, so there are no holes. But just so that we know we didn't forget it, we might just say no holes here. Now, horizontal asymptotes are all about the degree of the top and the bottom. So in this case, notice in the factored form, it made all of our other work really nice. But in terms of finding horizontal asymptotes, you would actually want to know what is the highest power on the top and the bottom. And in this case, we don't actually have to FOIL everything out. We can just think about it. The highest term in the top would come from multiplying this x term by this x term if we were expanding it. And that would give an x squared plus other things. We don't really need to know the other things, it's just the highest term. Now, secretly, this might just look like x plus 1, but it's actually x plus 1 squared, which is hiding an x squared term plus other things, right, if we actually expanded it. So then when we think about distributing this term with this x, we actually have an x squared times an x, which is going to give us an x cubed term plus other things. So this is kind of a shortcut of how you could look at the highest terms. Just look at the highest term at the top and bottom. And if you wanted to, another way you could do this is to expand it all out completely, and then it'd be very easy to see as well. But this is a bit of a shortcut. So here the highest power is degree 2. Here the highest power is degree 3. So in this case, the denominator has a higher power than the numerator. So looking back at our instructions for horizontal asymptotes, we are, in this case, the numerator's degree is less than the denominator's. So the horizontal asymptote is guaranteed to be at y equals 0. So horizontal asymptote at y equals 0. So we found all the information. Now we just need to graph it all together, and here we're going to take note of the multiplicities as we go through. Whenever you're ready to combine it all, I recommend that you first plot all the points that you found, and we might need to plot more points, but just from our steps 1 through 6, we found the x-intercepts and the y-intercepts. So I'm going to plot those at the very minimum. So I've got 0, 3. Okay. I've also got -2, 0. 3, 0. So first plot your points so you know where things are. Next, plot your asymptotes. They kind of give you an idea of the structure of the graph. For instance, we've got a vertical asymptote at x equals -1, so I'm just going to draw the dotted line. Also at x equals 2. And we've got a horizontal asymptote at y equals 0, so we're going to draw that. Now, horizontal asymptotes do not mean that the graph can never cross it. It just means as you go out in the negative x direction forever and the positive x direction, eventually the graph will start to approach that value and not touch, but maybe close to 0. As we can see here, it actually is going to cross it, but it's just later on that it approaches and has that asymptotic behavior. And there's no holes for us to mention, so we don't have to draw that on the graph. So the final thing that we've got to bring together is sometimes you need to plot a few more points to help you see things, and then the idea of multiplicities, which we're going to talk about. Now first, it's going to help you if you can see sections of the graph. That's going to help you see what's going on. For instance, starting at the left, going to -infinity, do we see we're going from -infinity and we are going all along in x values? I'm not saying this is what the graph looks like, but at x equals -1, there's a vertical asymptote. That kind of splits us into the values of x before -1, the values of x between -1 and 2 for our next vertical asymptote, and the values of x after +2. Now this is going to help us because this really helps us see that the whole graph can really be split into portions before -1, between -1 and 2, and after 2, just like we're seeing in our domain. And we're going to consider these going from left to right. So I'm going to start through values that are negative over here, and then we'll proceed to the right. We know the function crosses here, but it'd be important for us to know, was the function higher than the x-axis before that point or lower than the x-axis? So that tells me I need to find an additional point. For instance, let's find, this is -1, that's -2. Let's find the output value at -3. So off to the side. So using our calculator, we're going to carefully calculate this value. I recommend you type it into your calculator now, pause the video and unpause to check your answer. After evaluating -3 into our function, we get the output value -0.3. So that tells me at -3, the output is about here. Okay. So before our x-intercept of -2, we were below the x-axis. Now, what we're going to do is we're going to piece this together. Since we've got a horizontal asymptote, we know eventually the output value is going to stabilize towards the horizontal asymptote, and because we just found this additional point was below the x-axis, we know it's going to stabilize below the x-axis as opposed to above the x-axis. And now the behavior is eventually it's going to come and pass through this x equals -2, and this is where the idea of multiplicities come in. Because what's going to happen is the graph would either maybe pass through or bounce down. And although you could plug in points to verify this for sure, for instance, you could plug in -1.5 and know if it's above or below, that works. But a quicker way is to look at the multiplicities because it tells you the behavior of the function after it passes through a point. Specifically, what term contributed the x-intercept of -2? Remember, x-intercepts come from when the expression equals 0, which only occur when the top is 0 for a fraction. So this term specifically is what generated our x-intercept of -2, because when x is -2 and you add 2 to it, that takes this term to 0, which multiplies the whole expression to be 0. So this is the term that contributes this x-intercept, and we'd have to ask ourselves the multiplicity. Notice this term only occurs one time because it's only there one time. That's the exponent on it. For instance, this one is different. It's got an exponent of 2 for the x plus 1 term, but this has just one occurrence. So when the multiplicity is odd, it passes through the point. So it goes through the x equals 2, and it's going to pass through something like this. If the multiplicity is even, then it kind of bounces back. So if it had been even, it would have come to -2 and then bounced back down. But in this case, the multiplicity is odd, so it's just going to go from -2 and it's going to pass through. And since we know we've got a vertical asymptote here, the only way that we've got a vertical asymptote is if the x values get closer to this, we approach either positive or negative infinity. But we know it's got to approach positive infinity because terms right before it were positive. So we know our graph looks something like this. Now again, all of this could be determined if you evaluate the function at more points. If you want, it never hurts to find more output values. So for instance, you could look at f of -1.5, f of -0.01, and you could see both of these output values are going to be increasingly positive. So you can always plot more points if it helps you. And notice this kind of covers our behavior for the whole portion of the graph that is before -2. So now we need to turn our attention to the portion of the graph that's between -2 and 1. Okay. And again, we're going to look at multiplicities to help us find this. So the point of interest that we're looking at here is this vertical asymptote at -1. Think about what term in the expression created this vertical asymptote. We know vertical asymptotes occur when the denominator is equal to 0. So specifically, to get the vertical asymptote at -1, that occurred from this term here. This is the term that is 0 when x is equal to -1. And you need to ask yourself, how many times does this vertical asymptote occur? Based on this exponent here, it occurs twice. So the multiplicity for this is even 2. So what that means is for vertical asymptotes that have even multiplicity, you are approaching the same direction. So either both sides are going to positive infinity or both sides are going to negative infinity. That's how it works with even multiplicity. The sides of the asymptote are going in the same direction. So with that in mind, since we already know the left side of the asymptote is going to positive infinity, we're guaranteed, based on this multiplicity argument, the right side of the asymptote is going to positive infinity as well because it's even. Then we know it passes through this point here, which is our y-intercept. And I would say to know a bit more, we might want to plot an additional point. Notice we don't really know what happens after the y-intercept. So 1 is a point that's in between this range. So if we find the output value at 1, then we would be able to kind of get an idea what happens next. So let's plot the output value at 1. So we'll just want to calculate that here. So when x is 1, pause the video, find the value, unpause to check your work. And we get the output value 1.5. And if we want to have a bit more information, we can also plot Another point, if we want to know what's happening between 1 and our vertical asymptote at 2, maybe we'd pick 1.8, just some value in between, so we can calculate that as well. Now calculating this, I got close to 2.908163265. So if we're going to plot this, it's going to be very close again to 3. So what this tells us is our function goes down for some time, but then eventually starts going back up. And since we're approaching this vertical asymptote, we're going to assume this behavior continues, right? Because as it starts increasing again, it's going to keep increasing. And since we've got our vertical asymptote, we know it'll be approaching positive infinity to the left of x equals 2. So this clarifies what's happening in this portion of the graph. Next, we just have to identify what's happening in this portion of the graph, and we're going to use our ideas of multiplicity to help us again. Now we're looking at what's happening at this x equals 2 vertical asymptote, and you'd want to look back at the function and think what term contributed to that vertical asymptote. And do we agree it is this term? Because vertical asymptotes are what make the denominator equal to 0, and specifically the vertical asymptote at x equals 2 was caused because we had an x minus 2 in the denominator. Now what's the multiplicity of this vertical asymptote? Since the term only occurs once, the multiplicity is 1, and specifically that means it has an odd multiplicity. Now if you've got a vertical asymptote with odd multiplicity, that means the behavior before and after the asymptote are going to be opposite. So if it was increasing to infinity before, then it's decreasing to negative infinity after. If it was decreasing to negative infinity before, then it's increasing to positive infinity after. So think odd multiplicity about vertical asymptotes, the behavior is the same on both sides. Sorry, that's for even. So even multiplicity, the behavior is the same on both sides, but for odd multiplicity, the behavior switches. So since we've got odd multiplicity on this asymptote, and before it was increasing to positive infinity, after it's going to be decreasing, and we know it's going to come to this X intercept here. Now we need to know, is the behavior, is it going to bounce back down, or is it going to pass through? That's all about, first you could just plot points. For instance, this is at, where is it, at 3. So you could plot the value at 4 and see if it's above or below, that works. But if you want to reason based on multiplicity, you would look at the term that created this X intercept. So looking at our expression, X intercepts occur when the whole expression goes to 0, which only happens when the top is equal to 0, and specifically when x is 3, this term goes to 0. What's the multiplicity? The term only occurs once, so the multiplicity is 1. That means we're going to have a pass-through behavior. So at this x-intercept, instead of bouncing back down, which would happen if it's an even multiplicity, since it's an odd multiplicity, it's going to go up. But since we've got this horizontal asymptote, eventually the graph's going to have to pull back down to have this asymptotic behavior at y equals 0. And that's just a general sketch. Notice from the graph we can clearly see the x-intercepts, the y-intercepts, the domain of the function, vertical asymptotes, and horizontal asymptotes.